this video, we're going to look at 2.4 and 2.5. And in 2.4, you explore just one concept, this idea of the average rate of change. Now, you probably heard a lot about rate of change before. We talk a lot about the idea of rate of change in algebra courses, and you usually hear it in terms of slope. And we'll look at it as slope in the next section. But really, the idea of change can apply to any function. An average rate of change just says, basically do what you would do if you were talking about slope for a line, but with something that's a curve. And so here's our definition in math terms, is that the average rate of change of the function y, where y is equal to f of x, is the distance between where x equals a and x equals b, and for each increment that I change in from my x values, how much change happens in my y values. And so normally when you see it written in an algebra course, it looks a little bit more like this. You're changing your y values over your change in your x values. We call it an average rate of change because we're going to be looking at something that is not a straight line, but we're going to draw in a straight line, and that's my secant line. So if f of x is my red function down here, and I want to know, well, how much change happens between a and b, I can't find it out exactly in algebra, but if I kind of just draw in a nice little straight line like this, I can figure out how much I went up and how much I went over, and then that will give me my slope. And so we can use the formula, or I can just kind of count it out on here. And so if I have something like f of x equals a 4x squared plus 1. And I want to know the average rate of change between where x equals, let's say, 0 and x equals 2. I can say, well, when I plug in a 0, I get out a 1. And so 1 point on that curve is 0, 1. And when I plug in a 2, I will get out a 17. Right? Because 2 squared is 4, times the number 4 is 16, plus 1 is 17. So 217. Well, what does my rate of change look like between these two, my average rate of change, since this is not a smooth line? Well, that rate of change is going to be the change in my y values over the change in my x values. So 16 over a 2 or an 8. You could also do it in the reverse order. So if you said 1 minus 17 and 0 minus 2, you would get a negative 16 over a negative 2. Well, that's also 8. And so who gets to be A and who gets to be B, or who gets to be x sub 1 and who gets to be x sub 2 does not matter. What matters is if this is x sub 1, then he's got to be y sub 1. So if he's x sub 2, he's got to be y sub 2. These subscripts have to match, so that way you can keep the order the same in each one. But it doesn't matter who gets to be the first point or the second point. And that was really all that 2.4 talked about. You took that idea over to 2.5 and says, all right, look, we have a way in calculus to deal with an average rate of change when things are not smooth. We like to kind of just talk about it in terms of linear functions and where we talk about the slope of a line. Now, a linear function is a function that's in the form of y or f of x equals ax plus b, and more than likely you've always heard it as mx plus b, where m is my slope and b is my y-intercept. On the calculator, it doesn't use m, it uses a. So if you use any line reg functions, you won't see an m, you'll see an a. Anything that has x to the first power as its highest exponent, that's linear. So y equals a negative 2x plus 1. Y equals 4x minus 5. Y equals 2/3 x plus pi. These guys are all linear because x is to the first power. The example that we had before, the y equals 4x squared plus 1, not linear because he's got an x squared. The x to the first power has to be the highest power. If it's just y equaling a number or x equaling a number, you may or may not remember that these guys do draw lines, but they're not linear functions because they don't have x to the first power. They're just kind of like honorary members of the band because they draw lines, but they're not linear functions. Now, if I have something that's a linear function, let's take this negative 2x plus 1, I can graph this line pretty easily. Now, you can plug this into your calculator, but it's almost not worth it by the time you plug it all in. To graph this by hand, you can pick points out, so pick out x values, plug it in, and get out y values, kind of like what we did over here, where it says, all right, if x is 0 and x is 2, what are these points on the line? But there's an even easier way. You can begin at B and move according to the slope. So I am going to graph this guy right here, this negative 2x plus 1. So my B value is a positive 1. You start at that number on the y-axis. So I'm going to put a point right here. And then we move to the next point according to the slope. Now, slope very often just kind of looks like a number, but we always write it as a fraction. And so even though it says negative 2, I'm going to write it as negative 2 over 1, and this is my up and down, so I'll go up or down first. This is a negative, so that means go down. 1, 2. But we'll always run to the right. And so as I say rise over run, and I know I spelled rise wrong because I put a y in, but that means, so you're going to deal with the up and the down first with your top number, and then run to the right usually here. Can you run left? Yes, it just doesn't happen a whole lot. And so I went down 2, so now I'm here, and then I got to run 1, and I make a little dot. And if you want to do it again, you can. But 2, maybe 3 points is certainly more than enough for a line, and I'll give myself a little bit more space. And there he goes, and there's my line. So easy enough to graph. If I wanted to graph this one, pi is about a 3.14, so 1, 2, 3, and a little bit more. So I'll begin there, and then I'm going to go up to, and so up 1, right, so I'm a little bit here, up 2, and then I got to run 3. 1, 2, 3. And there's my line. Which, by hand, is really pretty easy. Now, I'll have to graph a few of these guys in WebAssign, so I have that pulled up right here. And so you got to pick the line tool, and then you're going to start by putting it on the B. This is written backwards, so this positive 3, we're going to start right there, make a little dot. Now, we're going to, after that dot, we're going to follow our slope. Our slope is a negative 2, just like what we had before. So I'm going to go down 2, run 1, and make another little dot. And then I think I have to click on it, yep, a little bit so it kind of like locks it in. And then you could check it. Well, what's the slope? My slope is a negative 2. And if it asks for the B value, which it does not, then I would type in a 3. And so this is kind of bad form. We usually like it in the mx plus b form where my x is first, but sometimes they kind of do move these things around a little bit. This one starts at a negative 16, so I'm going to click my line and go down to the negative 16. And then I have to go down 10. Uh-oh, I can't go down 10 enough. So this might be a good time to run the other way. So if I scoop that negative from off of the 10 down to my 3, I could say, well, now I can go up 10, so go up to the negative 6, and instead of running to the positive right, I'll run to the negative left. And I'll put him there, and then I'll click on that. And my slope is a negative 10/3, which is the rate of change for my function overall. It's not an average rate of change because this is not curvy. I don't have to, how do I get from one point to the next always looks the same. I don't have to take a different number of steps like we would have had to do on this one. So I can also, from the graph, go backwards and say, well, what does the line look like? And so I can do this a couple of different ways. I can count out my slope and say, well, if I start here, and I'll let you be my x1, y1, and he'll be my x2, y2. How do I get from one point to the next? So I'd have to go down 2, and then run 1, 2, 3, 4. And that would be my slope. And I can reduce it to a -1/2. I can look at my y-axis and say, well, where am I going through my y-axis? Where's my y-intercept? That certainly looks like a 1/2. So a good guess would be that it's a -1/2 x minus a 1/2. But we could also find it. We could say, well, I know that the form of a linear equation is y equals mx plus b. And conveniently, we know what m is. We just found it. It's a -1/2. And I have an x and a y. In fact, I got 2. I can pick my favorite, which is officially him now, and plug my x in and my y in, and now I only have to find b. And so I have 0 equals a negative times a negative, which is a 1/2, plus b. And I can solve this equation pretty easily now. And it is definitely a 1/2. Some of them are easier to see than others. Then I give you a graph at all. They may give you a situation that they want you to model and then find out an entirely different value. So this is from the slide, the last slide in 2.5. Water's being pumped into a pool. It's going in at 5 gallons per minute. Rate is important. So when you hear those lengthy words like rate, that's kind of when your flag should go up, that I want to pay attention to that. The pool already has 200 gallons of water. We didn't cover it during the last rainstorm. It's summertime. I'm just going to fill it up. It's already got 200 in here. I want to find the linear function v that models the volume of water in the pool at any time. If the pool has a capacity of 600 gallons, how long does it take to fill up the pool? All right, so how much water is in the pool? Well, I'm putting in 5 gallons every minute, and I already had 200 when I started. So in 1 minute, I'll have 205. In 2 minutes, I'll have 210. In 3 minutes, like that. So here is my situation of how much water do I have in the pool at that time. Well, how long then, how many minutes is it going to take me to get up to 600? You put it on 600 and this guy is going to overflow. So the maximum volume is 600. How long will it take me to get to that? And then again, this is going to be easy enough to solve after all that equation work we did in chapter 1. If I subtract 200 from both sides, and then divide both sides by 5, we can see that it's going to take 80 minutes, that's a long time, to fill up this pool. Or an hour and 20 minutes, right? Because I got, well, not hours, 1 hour and 20 minutes since there's 60 minutes in an hour. And so I can build models from just words. I can build models from a picture that I have, or if I already have the model, I can go ahead and graph it. If I was going to graph this guy on my calculator, just to remind you, you would go into y equals, type in your information. I think it was a +1. That was -1. And when you hit graph, there he'll go. Now, if you're in a situation where you have the model and you want the picture, but they want points, remember you can hit second table, and you'll get all those points that are on the line. And so this is 2.4 and 2.5.